Hello, everyone. Good day. My name is Victor, and I'm here to talk about automation and process control. If you are a student, you are an engineer, um, that is a fresh graduate, or a relatively uh, young engineer, and or you are trying to understand how automation and process control in the industry works. You want to have a practical understanding of how industrial automation works, then this is the right place for you to be. If you're interested in a content like this or contents like this, please do well to subscribe to my channel. It's on YouTube. And yes, I'm going to be introducing a lot of topics on automation and process control. If you are a mechanical engineer or engineering student, electrical engineer, systems engineer, mechatronics engineer, chemical engineer, or whatever um, field you find yourself, and these kind of topics interest you, yes, I guess this is the right place for you to be. And today, we are not just going to look at the theory, we are looking at the practical aspect of it, how you can relate on a practical level with automation. For example, today we'll look at how you can program uh, a PID control. When someone says a PID control, what does it really mean? And how can you take advantage of this knowledge? How can this knowledge help you? So that is what we'll be looking at today. So without wasting any of your time, let's go. Let's get to it. Now, first of all, I would want you to I want us to look at automation from the very basics. If you are a chemical engineer, you relate more with this, and I'll tell you why. Now, let's assume we have a mixed flow reactor. A mixed flow reactor. Let's say a mixed flow reactor. Sorry. Okay, let me go back a little. And try to take this out, get an eraser, and take this out. Go back. Sorry, I have a call. I can't pick the call now. Okay, I'll take my pen again, and I have a mixed flow reactor, and we are going to be looking at what we mean by a mixed flow reactor. This is a mixed flow reactor, and why today the topic we are going to be discussing is more on control engineering. We're looking at process control, industrial process control. We are going to look at this, a typical feedback control system. Then in our subsequent videos, we might look at other forms of automation and also SCADA, and also how to program PLCs and HMIs as SCADAs as well. Yep. But for now, our interest is on process control and how to tune PID controllers. PID controllers are the most robust and the most effective form of controller that there is, and the tuning of this controller is another science of its own. Now, basically, we have this, and there is a stirrer. So here we have a stirrer. We have an inlet into the system. We have an outlet from the system. From here, we have an outlet from the system. And now let's assume we have a reaction. This is talking about a reaction, what a chemical engineer can relate more with, but every other is not a difficult something. I just want you to understand the foundation of this before we look at how it works so that you can better appreciate what we're talking about. So we have a reactant A or a raw material A that is being processed into, say, another raw material B. And this will make you appreciate what you are controlling, because if you don't know this, you might not really appreciate what it is that you are trying to control. It's very important that you know this. Now, let's assume also that I'm trying to, we have a feed. I'm trying to monitor the raw material, which is the reactant A. I'm trying to monitor it and how it goes. And let's assume the volume of this reactant, this reactor is this. And after everything, we have our products also coming out, F. We'll call it also A. But you agree with me that if there's a chemical reaction inside the tank, inside this vessel, that some of the A will be used up and we cannot have the same quantity here. So the initial quantity we have here, we can call it A naught. That is what we had initially that goes into this. And after a while, we have A final coming out. And this A final is the same thing as what we have here, because we assume that this tank is perfectly mixed. It's perfectly mixed. So what is coming out here is also Fa. Now, let's assume that there is a reaction taking place here. The reason you are doing this will become clear very soon. It's not going to be long. I'm not going to take your time such. We want to do a material balance for this. That is, we know that in ordinary chemical reactions, in everyday life, you cannot create material as in mass, neither can you destroy mass. So the total mass that you have before your reaction began is the same mass, total mass you will have at the end of the reaction. So you can't create nor destroy mass in everyday chemical reaction. Of course, a nuclear reaction is something different. So we'll say that our input minus our output is equal to in what we are generating by reaction. Okay, what is being created because of reaction. So reaction, what we are creating by reaction, plus what is accumulating inside the system. What is accumulating? That is the accumulation inside the system. What is accumulating inside the system? But for a mixed flow reactor, as there's no accumulation. That is, what you are saying is that I can't find, I don't know where the cursor is again. Okay, yeah. So for what we have is that we have a constant volume. So the volume is constant. We call it volume V. It's not the volume of the total reactor, but volume of liquid inside the reactor. That's what we call the volume of the reactor. So the volume V, we assume it to be constant. And because of that, we can say that there's no accumulation in the system. So this accumulation term here, the accumulation term here becomes 0. So what we have is that the inputs minus the output is equal to the reaction. So if we solve this further, we'll have that our FA, which is input, what we have here, our input here, minus our FAO minus FA is equal to the reaction. So the reaction term, because there's a consumption reaction taking place, we put a negative sign. That is, the amount of A that we have is reducing due to the reaction. We put a negative sign. So minus RA times what's the volume of the reactor, because the units of the units of this is as of this flow rate is number of moles per unit time, as is mole per minute per hour per second. Yeah, and the units of this is moles per volume per time. So in order to take care of the volume term, you introduce another volume. So dimensionally, this equation is correct. So what we are saying in essence is that this expression is the difference in the concentration of A before the reaction and after the reaction is accounted for by the reaction inside the tank. Now, I don't know, this is disappearing. I can't find the okay, yeah. So now we also know that there's a term called conversion in reaction. The conversion is simply how much of your reactant has been converted into product. So it is between 0 and 1. The value is between 0 and 1. That is in percent. 80% of the reactant has been converted into products, or 8% of the raw materials have been converted into products, 70% have been converted into products. So that was basically what we're talking about here by conversion. And that is simply put what we started with, which is FAO minus what we ended with, which is FA, amount of A that is left. Then we divide all that by what we had initially. So it therefore, from this expression, it therefore means that our FAO minus our FA, the FA we have here, is simply put FAO times FAO times XA times the conversion times the conversion. And that is to say that this expression we have on top here, I don't know, this expression here, this whole expression here, this whole expression that we have here is equal to this is equal to minus RA into bracket V into bracket V. So from this expression, what we see is that if the flow rate, this feed rate, FAO, is constant, from here, let me just go up somewhere here. Okay, let me go up there. From this place, we see that XA, provided that the feed rate is constant, XA, which is the conversion, varies directly as what? The volume of the reactor. This is what I want to establish. That's why we are doing this. This is just what I want to establish. That is the conversion, how much of your raw material that is converted into a product is proportional to the volume of a product. So that means as an engineer, as a process engineer or as a chemical engineer that is in charge of ensuring quality, and also, you know, on one hand, you are trying to ensure that the quality of the right quality is maintained, and on the other hand, also you are trying to save costs for the company. So you can see that the conversion varies as for this mixed flow reactor, the conversion varies as the volume of the reactor. The larger the reactor, the larger the conversion, and vice versa. And what it means is that if the company, for example, has fixed a conversion, let's say 80%. I don't know why I like using 80%, but let's assume the company has fixed a conversion of say 80%. And probably there's a tolerance that's anywhere from 75% to 85% will do. Because from this that has been given, the profitability of that venture, of that production, has been factored in. So imagine you are producing a 90% conversion, for example. Now, on the surface of it, it's very good for you to produce kind of conversion, but at the other time, at the other end of it, it might be costing you more time, more energy, more resources, because you have to pump in more water or more liquid into the system. So the additional cost you incur in trying to over purify your product might make you not to be competitive. So at the end of the day, it is important that you maintain your reactor at the desired value. And this desired value is what we call the set point. The set point. Can you see? Okay, the set point, that is SP, set point. That is what we desire. So in this case, our set point is 80% with a tolerance, that is with a lower tolerance of 75% and an upper tolerance of 85%. So we have about 10% tolerance in between. So anywhere between that is fine. So that is what you as a process engineer or process control engineer will try to establish, that you are always producing your product within this range, within this limit, 75%, 85%. It doesn't have to be exactly like this, but you get the whole idea. And then you now have to decide, or sometimes, you just got the machine, you bought them. There are companies that build these machines. Now, if you end up working in these companies that build the machines, then of course, you have to look at this from this perspective. Then you decide, what kind of control architecture am I going to use? Am I going to use a simple feedback control setup? Am I going to use a feed-forward control setup? Am I going to use a feed inferential control system? Am I going to use a cascade control system, ratio control, or what kind of control am I going to use? So that is what we are going to be looking at. So the next thing we'll look at is, because this video that I'm about to show, this simulation video that I'm about to show is talks about let me get this video. Where's my mouse? Okay, my mouse is finally working again. Okay, so this video we are about to talk about, this is a simple feedback control. But before you really will understand what a simple feedback control is, or what a PID control is, let me just give a brief description of what a PID control is. And you see, we talked about set points. You see, this is the set point. This is the process value. This is the set point. I don't know if you can see what I'm trying to show here, but okay. I don't know if you guys can see. This is the process value. This is the set point. This is the proportional gain, integral gain, derivative gain, and this is the highest value that can be measured. As is in this case, it is this tank here you are looking at. We are looking at 300, and the lowest we are looking at, say, 0. So this is what we are trying to do now. But before you understand, before we look at this, I want you to really understand what it is we are trying to do here. Okay, you can see 0 and 300. I want you to know what a PID controller is, what it can do, and all that. Okay, so we'll go back to my notes, and we'll look at something again. And this time around, okay, let me use my, just a moment. Okay, so we are here again, and okay, so we are going to take look at a simple feedback control setup. We have our process, which is the tank we just described now. So we want to measure the level of liquid inside this tank, and one way we can have a level sensing device. It could be a radar device. It could be a probe. It could be a radar, a probe, and it measures the level of liquid inside the tank, and it sends a signal out. That signal can be in terms of voltage, 0 to 5 volts, or 0 to 10 volts. These are the most common. Or it could also be in terms of amps. So we have like 4 milliamps to 20 milliamps. So the signal that is coming from this sensor could either be 0 to 5 volts signal, 0 to 10 volts signal, or 4 milliamps to 20 milliamp signals. And there's a reason why, for example, this is 4 and not 0. It has its advantage, and that's what we'll look at maybe in another video. There's a reason for that. Or just to tell you, so that in case there's breakage in the line, you can be able to differentiate between a fault and a low level measurement. That is when the tank is empty or when there's a fault. But in these other ones, it might be difficult for you to find out, because it might give you 0 and you might think that the tank is empty, whereas it is 0 because there's a breakage, there's a cut in the line. And in this case, you might not be able to distinguish that when you are using 0 to 5 volts or 0 to 10 volt signal. But with 4 milliamps to 20 milliamps, you can tell. When it is 0, you know that you cannot have 0, so something definitely must be wrong. So when it is 4 milliamps, it is empty. When it's 20 milliamps, it is full. Now, this is the sensor that we have. This sensor brings a signal. That signal has to be sent to a controller. It has to be sent to a controller. And the controller is something like this. This is your controller. And there are different types of controller. We have on-off control. We have PID control and different types of controllers. Okay. Now, this controller, I intentionally did it big because I want to explain something as well. I don't know if you can see. Okay, yeah. So I want to explain something. The signal, this whole place is the controller. It always happens inside the controller. That's why I'm taking my time to pull that. Here we have what is called a summer. They call it a summer or a comparator. What it does is that this signal that is coming from the sensor is sent to this comparator, and it is, here could be a plus, depending on the conversion you are using. Could be a plus, and here could be a minus. And then the signal that comes out now goes to the control head. That is where the actual control is happening. It could be a P controller, it could be an I controller, it could be a combination of all or a part of them. That is called a PID controller. And all these, most books will separate them, but actually these are all happening within this system. So they are all the controller. So what does the summer do? The signal that comes from here, the signal that comes from here, okay, and here we have what we call, here we have what we call the set point. The set point, like I said before, is what you intend to achieve. In this case, we are, the set point, we give ourselves 80% conversion, and that 80% conversion corresponds to a particular volume, V. Okay, it corresponds to a particular volume. The volume could be, let's assume the total volume of this tank is 500 liters or 300 liters, as the example you are about to see. Say it's 300 liters, and they want to keep the volume fixed at, say, 200 liters, for example. At 200 liters. That means your set point here is going to be 200. Set points is going to be 200 liters. And these 200 liters that you have here, if you are using a 0 to 10 volts controller, like this example, that's what we saw here. This, you can do an, what's it called? Okay. You can do an interpolation. We know that the highest value you can have here is 300. The lowest value you can have is 0. And if we're using a 0 to 10 volts signal, we have 0 and what? 10 volts. And here we are interested in 200. Our set point is 200. Now, what is the equivalent of 200 here? We can call it x. That we can solve for. So we can say x minus 0 over 10. That is x minus 0 over 10 minus 0 is equal to, we go to this place, 200 minus 0 over 300 minus 0. So at the end of the day, we have 2/3 times 10. So your x is equal to 2/3 because, 2/3 times 10. 2/3 times 10, which is 20 over 3. And 20 over 3 is roughly 7. 20 over 3 is roughly 7 because 21 over 3 is 7. So just take, so it's approximately 7. So we talk about nearly 7 volts. Okay, nearly 7 volts. So what is going to happen is that if your set point, so the standard, what we have here, the SP, I don't know if you can see. Okay, yeah, our SP here, we said is 200 liters. And that 200 liters in terms of current is 7 volts. And what is coming from this signal up here? This signal, what is coming from this signal up here will be measured against the 7 volts. For example, if we have 6 volts coming from here, 6 volts coming from here, 6 volts and 7 volts are not the same. So what's going to happen is that it's going to be, it's going to compare them, then it's going to send a signal. That signal that it sends here is called the error signal or error. It's called the error signal. So this error signal is telling you, okay, we have 6 volts here. That means it's not yet full. It's not yet up to the level that we want. So please, to tell this PID controller to open the valve more so that more liquid can come in. So the question is, what valve is being opened more? Now we looked at, let me say, here we have a valve coming in here, okay, and we have another valve going out. Okay, so we have, this is a valve, this is a pneumatic valve. The pneumatic valve is valve that is actuated by air. This is also a pneumatic valve. So we have a valve. So because we have an error signal, this error signal is sent back to this valve. Now, but to do that, sometimes we might need what is called a transducer. A transducer. Let me, I guess I have to write it. Let me not be lazy and do it. Hey, I can't find my cursor. Okay. Okay, let me make it a little bit bold so that at least I'll not be struggling to find. Okay, how do I do that? Color and thickness again now. Okay, let me make it a little bit so I won't have to be looking for it all the time. So yeah, I think it's better now. Now, so we have a transducer. Let me erase the spelling of transducer. Nah, sorry. I'm still getting used to writing on the screen. Okay, the little mistake I made, let me take it off. And also this transducer spelling I wrote here. Okay, go back. So we go back to draw. This is another work on its own. Okay, so basically, yeah. So this is small again. Why? So you have a transducer. Let me make it large again. Thickness, and I think this is fine. Okay. Yeah, I want to be seeing this carefully. Yeah, so we have a transducer. So a transducer, that is that. Now, this transducer, what it does is that, for example, this is operated by air, and this is electric current. So this transducer changes the signal from current to um, um, to air signal. So this can be current to air transducer. So this is current to air, as in current to pneumatic transducer. Air is also pneumatic signal. So you have a pneumatic signal. Usually it is represented by broken lines. This pneumatic signal is represented by broken lines. So it comes here to this valve. So the valve will be used to either open the valve or close the valve depending on what is required, and also depending on the type of the valve, whether it's an air to open or an air to close valve. We have what is called an air to open. You need air to open the valve, okay, and also have air to close, an air to close valve. So depending on the type of the valve and also what the error signal is, this signal coming from the controller will tell the valve to either open or close. So basically that is that, and this is what is referred to as a feedback control signal. This is what is referred to as feedback control. Okay, now this is what is referred to as feedback control, and we're going to look at sorry, I'm trying to find something. Okay, so this is what is called the feedback control. So what's the feedback control? In a feedback controller, you allow the disturbance. The disturbance is the change, the fluctuation. Yeah, you allow it to enter the, for example, this line. Yes, water is coming in or liquid is coming in, but it might not be constant, might not be steady. There might be a pressure drop suddenly. There might be a fluctuation in maybe probably the current to the pump that is pumping in the liquid might fluctuate, and this might also affect the RPM of the pump and also can result in fluctuation. And this fluctuation is what is called a disturbance, and it can enter into this tank. So, but before you are able to make any control action or take any control action, this disturbance has already entered the system. Then your probe will sense it by change. As is, for example, you want it to be at this level, so it might either drop or it will increase. And this is a disturbance that you want to correct. You don't want it. You want to correct it. So your signal picks up. So your sensor picks up this signal and sends it to your controller. And your controller takes control action to either close or open this valve. So it is the closing or opening of this valve that is used to restore the level that you want. That is what is called a feedback control. In a feed-forward control, you don't allow the disturbance to enter into the system for taking control action. So, but feedback control is the more common of the two, and these are the two extremes of control: the feedback control and the feed-forward control. But there are other types of controllers also. We'll look at them in our subsequent classes, and what their advantages are. For example, we have a cascade control. A cascade control is a combination of these control types. So we'll look at that. But now let's go back to what we are discussing, which is how to control volume in a tank, how to fix the volume in a tank. Now we are going to look at that. Okay, so we go back to this. So here you see we have the program. This is factory IO, and this is uh, the programming side of it. It's based on the functions block diagram. This is called control IO. So this comes with the product, and yeah, we're going to look at that. So here we're going to start our you're going to start what I was saying. Yeah. So this is the pneumatic valve we saw just now. This is the pneumatic valve. This is the outlet valve, and you use air. When the air comes from under, it pulls this rod up. It's called the actuator. It pulls it up, and it opens. Probably it could be a gate valve or something. It opens it and allows liquid to flow out. And if it's an air to close valve, the air comes from on top. There's a diaphragm here, and it pushes on the diaphragm pushes on this, and it closes. So it could have air to open or air to close valve. So depending on the configuration, and they all have their advantages and disadvantages. Now, you can see our system has started, and okay, I'm going to stop it again and run it. So you can see here it's open, but nothing is happening because I haven't done the set point. I have not fixed the set point. But the moment, the reason this is opened is because if you look at here, I'll check, let me dock all tags. You see, I've already opened the discharge valve. Now, if I close the discharge valve, you can see this is also a 0 to 10 volts signal. So that's why I'm saying 0 to 10 volts here. You can see 0 to 10 volts. See? So the level to which I open it, it depends on, as in, affects how much this valve is opened. If I open it a little, you can see. So that's I left this open so that I can monitor and see how well the controller is working. So that is that. Now this is the set point. The set point is what I want to achieve, and it's also from 0 to 10 volts. But in the program, as you can see, I've done some things here. I've done some conversion to make sure that it tallies with the 0 to 300 liters that we have here, or 300 centimeters that we have here. So I'm assuming that each centimeter corresponds to a liter. So I'm assuming we have 300 liters capacity tank. But what is more important is just get the concept, not the actual value of what we have. It's just an example. So I'm going to take the set point. You can see I've taken the set point. No, I don't want it to be 10. Okay, it's 6. The set point is 6 here. So if I go to my controller, because I'm measuring to 300, if I go to this controller here, if I go to here, you'll see that the set point is around 178.6. That means it's not exactly 6 here. Here you will see the value more correctly. The value from the set point is 5.94. You can see 5.94, and it's multiplied by this factor because the highest is 10. So 10 times 30 is give me 300. So that's why I have this factor here. And as you can see, it's going to fill. The tank is going to fill up, and when it gets to a particular level, it will empty. Now let me dock. Okay, clear all dock tags. So you can see it's going to be fluctuating around this set point of 178, almost 180. If we zoom into this, if we zoom into this, we see our set point is around 178, 178.6. That's around 180. But you can see that it's going up and down, up and down. So you want it to be as close as possible to the set point. But mind you that systems have their own inertia. Just like we have inertia in physics for moving bodies, there's also inertia in terms of heating and everything. And also it depends on the response. The response, as in how fast your controllers respond. And so there's going to be some delay, some lag, and this can affect all that. And the whole thing, and the thing is that you don't want it to be too exact, because if it's too exact, any little fluctuation will make your You see, if you look at this now, you see it's opening and closing. Now it's closed because now the tank is emptying. It has opened. Now, if it's too exact, the frequency of opening and closing will be very, very high, and this thing will pack up in no time. So that's why you have to give tolerance. Like in our own case, in the example we looked at before, we talked about 75 to 85% conversion, and that is enough. That is enough tolerance for you to be able to keep the health of your pump and your control architecture. You can see this is a probe. This is a probe that is used to measure the liquid level in the tank. And one way you can control that, like I said before, your PID controller is a proportional, integral, and derivative controller. It's a kind of control system that is used that it gives it takes advantages of all three control. It's another video on its own. We'll look at that in subsequent videos. But just know that there's something called the PID controller, and for this controller, let me scroll here. This is the PID controller. You have the process value, you have the set points, you have the gains, the proportional gain, the integral gain, derivative gain, and your high and low values, the maximum values that you can have in the system. Now, what control engineers do is to set up this. Look for the values, how you can find the values for these controllers. If you can do this, you are a big boy. You'll be in money. You'll be sought after, because for you to be able to design a PID control system, you must be able to know the system. You're supposed to understand the system, write models, as in develop models, and solve them, and also see how you can get their there are a lot of mathematics involved in it. You need to get their Laplace transforms, and you need to get their transfer functions. And these transfer functions, some of these things are not they are not linear, so to speak. It's not every physical process, every industrial process that you can reproduce mathematically, but there are softwares that you have, and there's some systems like Siemens and the rest of them that have incorporated the ability for you to automatically tune the controller, so it will generate values for you, to generate the gains for you, the proportional, the integral, and the derivative gains for you, and you put them, and to a large extent it will control the system, because it has a history. As the process is running, it keeps a history, and there's some softwares also that do this. There are some people that offer this. They get a history of your production, and with that history they make a plot, and then they solve for the best solution based on that, so they can get an approximate equation that they can use to predict the gains that will be needed for the reaction for the system to perform optimally, at least at the best way possible. So basically there are solutions like that, but this is essentially what it means when we talk about process control, and it's a very, very important discipline, and it's very, very important. And also the safety of chemical plants, the safety of investment, the safety of the environment lies on how well you can control a system. If your system is not stable, if your system is unstable, it's a dangerous situation. Imagine this is a nuclear reactor and it's unstable. Once the criticality of the reactor is more than 1, that is an explosion waiting to happen, because we have thermal runaway. And the same vein, in most heated or pressurized systems, you don't want your system to be unstable. You don't want it to be that, because if it's unstable, then it can get out of hand and it can cause serious explosion and problems and loss, not only to lives but also to the environment, to even investment and all that. These are things you want to guide against, and that's why it's very important that we understand what control is about, what control system is about. And this is just an introduction. If these are the kind of videos that interest you, if you want to learn more about process control, industrial automation, you want to look at conveyor belts, how they work, how different kinds of sensors work, actuators, how they work, then I guess you have to subscribe to this channel. And that's what I have for you today. Thank you, and have yourself a nice day. Bye.